Ladies and gentlemen, we're about to start. So I would like to welcome you to the last IMO showcase lecture. Today we will have Vlad Matei from the Simion Stoilow Institute of Mathematics of the Romanian Academy from Romania. Vlad has been with us since last year as an instructor at the IMSC. Let's welcome him.
What I want to tell you is, as usual, an IMO problem. But what I want to start from, so let's start from the statement of the problem. Let's see if this works. Okay, so let me start from the statement. Okay, so you have a convex polygon in the plane. You know that the vertices have integral coordinates, and they are on a circle. And S is the area of the polygon, and you are given an odd positive integer such that the squares of the sides. So you're given an odd positive integer such that the squares of the side lengths of P are integers divisible by n. And you want to show that twice the area is also divisible by n. So why did I specifically chose this problem? Because just from the statement, you might wonder, you have something about sides. You have vertices on a circle. So you have a cyclic and k-gon in this case. So one question you can ask is there any specific relation between the area and the side lengths of the polygon? So why would that actually be something that's meaningful is you already know some formula. So for the case that you have a triangle, there is a formula that everybody knows, and it's used in so many places. Namely, you have Heron's formula. But let me tell you another formula which is not that known, and some of you might know it. So if you're in the case k equals to 4, and you have a cyclic quadrilateral, sorry, that's a typo. So that's a cyclic quadrilateral. Then the area, you can compute it by this formula, okay? So there is a very nice formula that uses the side lengths, and it's this expression. Okay, so for 3 vertices, you have a formula. For 4 vertices, you have a formula. The question is, are 3 and 4 the only cases for these kind of things? Like, is there any way to get at a formula? So, I mean, this is the way I am starting to think about this because I'm doing research. You would, when you start with a problem like this, you'd say, okay, I have a reason for 3, I have a reason for 4. I have some formulas. Maybe there's something general going on. I mean, you wouldn't do this in a contest problem. You probably wouldn't start here. But it's one of these problems that makes you wonder whether there is actually a formula more general than this. Okay, so let's start getting at this. So it's natural to wonder if there's actually a more general formula for any cyclic k-gon. And actually, this is something that's been studied. Okay, so let me justify that there is some sort of formula. So what's the setup if you want to do some sort of formula for computing this out? Well, let's do some complex geometry, since some of you had lessons on complex geometry. So let's take some complex coordinates for the vertices. These are z1, zk. Okay, r is the circumradius because everything is on a circle. And I'm going to take qj to be vj plus 1 over vj. And the convention is when I write vn plus 1, that's equal to v1. Okay, so it's a cyclic notation. And now you can compute everything out in terms of these numbers that I've written. Namely, the square of the side length is r squared times this complex number, which is 2 minus qj minus 1. And for the area, you have what is called the shoelace formula. So that's one way to state it. I think there is another Russian name that I can't recall for it. I think Kirill Dochev formula or something like that, but shoelace, I think, is the most convenient way to call it in the literature. So that's one way to compute the area in terms of these complex numbers. And there you go. You have that our area is also expressed in terms of these quantities qj. So the numbers ak squared are in terms of r in a single qj, and the area is in terms of r and all of these numbers mixed together, okay? So you have all of these things. And now let's put them together. So let's see what would be the reason to put them together. Well, you have n plus 1 quantities, which are the area squared anyway, multiplied by 16, and the side lengths, ak squared. And these all depend on these variables, which are r squared, and these q1, qn. And also, the q1, qn, they are algebraically dependent, because if you remember, the qj's are vj plus 1 over vj, so obviously their product is 1. Okay? So that means the word for it is that these numbers are what are called algebraically dependent over the rationals. So that means there is a polynomial formula that is verified by all these numbers together. Okay, so, okay, you know that there's basically some relation. I mean, but this is not something you would be satisfied with having. I mean, there is some relation, but if you can't describe it precisely, it's not going to be useful in these sorts of problems. Okay, so we know that, again, there must be a relation, because, again, you have n plus 1 is like in linear algebra. You have n plus 1 variables, I think n plus 1 equations, and n variables, they're going to be algebraically dependent. Okay, it's the same idea. Good. So there was a more precise conjecture about this, namely that the area squared must satisfy a monic polynomial which has this precise degree, okay? It's something combinatorial, this degree. It's pretty large, as you can see. And the coefficients are symmetric polynomials with integer coefficients in the squares of the sides of the polygon, okay? So this is the more precise way to state what the relation should be between these guys, the side length squared and the area. And this is for an odd number of sides, and for an even number of sides is actually something a little bit different, because you need to introduce some signs on the sides. I won't go into this detail. It's not that important. But again, there's a precise way to describe what this is. Okay. So let me state what that one is in a mathematical precision, okay? So you have this result that, okay, there is this polynomial which is encoding the area and the side length squared, and this gives you 0. And moreover, this polynomial is homogeneous. It's symmetric in the aj squared, and it's also irreducible, okay? So these are some nice properties of this polynomial. Again, it's not something explicit, okay? We know that this exists, okay? Good. So let me actually give you some explicit formulas so you see what we're kind of looking for. And, I mean, these are already hard to prove. I mean, it takes a little while, but you have these sorts of formulas for a cyclic pentagon. You can compute everything in terms of the sides. And actually, if you do the substitutions, so you see that the variable that I'm interested in is what? Well, u is 16 times the square of its area. So I'm looking at that expression as a polynomial in u. And if you unravel all the notations, the degree of it will be exactly 7. Okay, so what I want to point out is that this matches this number here. Okay, so if you do 5, you plug in 5, it should give you 7 for that one. Okay, so that's the degree of that polynomial. And let me show you one more formula. Okay, this is even a bit uglier. So again, there are these T2, T3, T4, T5 that you have. And you have these elementary symmetric functions. And again, you can write out this polynomial. Again, it has the correct degree predicted here. Okay, so that's the predicted degree of it. Okay. And actually, we know some properties of this polynomial. So these were proven in some papers in 2003. The degree that, in general, was proven by Igor Pak and Fedorchuk in this paper independently by 3 other people. But other than that, I mean, sorry, let's go back. So other than the pentagon and the hexagon, I haven't checked. We don't have explicit formulas, I think, for heptagons, octagons. So, you know, there's all these things that, you know, people might be interested in looking at, you know, finding explicit formulas for other ones. I mean, describing precisely what this polynomial is. Of course, having this, you can easily solve the IMO problem if you would have this available as a tool. So I won't go into precise details. It's not a complicated thing. But I just want to point out that from this general fact, the problem would follow. Okay, just using the fact that you have this monic polynomial in the square root of the area and these guys, it's enough to give you the problem. Okay, good. So, I mean, that's about philosophy. And now let's actually try to solve the IMO problems. So you'll probably not approach the problem in this way. So let me find the pen. So let's start thinking about it in a different way. Okay, so let's think about the problem, how you would think it during a contest, not like a research problem. Okay, so how to do it. Okay, so what do we know? So let me actually switch to the problem now because it's enough about polynomials and so on. So let me go to the statement again. So we have it there. Okay, so firstly, we can reduce. So first observation, we can reduce to prime powers. Okay, so we can assume that n, the n we're given, is obviously a prime power. Let's say a p to the t. And the main idea is to try to do induction. So try to do induction on K. So, I mean, in all these geometric problems, how would you go about doing induction if you have like a combo geo problem? Well, if it's talking about area, maybe we should be looking at the diagonal. So let me draw the picture. You have here, you know, your polygon A1, A2, A3, A4, A5, and so on. So what's the idea for induction? Well, if there is a diagonal whose square is divisible by p to the t, then I can obviously, whatever here. So I have a1, ak. So my diagonal is somewhere, I don't know, here. So if I have this diagonal, then I get two pieces, right? I get 1 and 2. I get two pieces. Where I can apply induction. So I can apply the induction hypothesis. Okay? So this is what you would naturally do in a lot of combo geo problems. You triangulate, you try to divide it into two smaller bits and try to handle each of these bits independently. But again, what happens if you're not lucky? Because this is the hard part of the question. So, so what happens if you're not lucky? And in this case, it means no diagonal square. So is divisible by p to the t. Oh, one thing I should say, and it's already contained there in what I wrote, is that the area, obviously, by the shoelace formula, 2s is an integer, right? This is an obvious thing because you have the shoelace formula. Okay? Okay? So if you put coordinates on these points here, x1, y1, x2, y2, x3, y3, and etc., for each of these triangles, you can write out the determinant from the shoelace, and you get that twice the area is an integral number, okay? Okay, so that's one small detail, but you have to write it in the solution, obviously. And as I said, again, here, you just divide it to two pieces and you're done. So now, how do you deal with this case? So no diagonal squared is divisible by p to the t. So what's the idea? Well, let's start looking at the diagonals. So again, it's a, okay, so here you have a1, a2, a3, a4, a5, and so on. And I would say the idea is pretty tricky because what you try to do is you're looking at all the exponents of p in these diagonals. So you're looking, so we will look at Vp of a1 aj squared from 3 to j to k. Okay, so on the other side you have here k. So I want to actually look at all these valuations, and what turns out to be true, and this is the hard part of the problem, is if I assume that p to the t does not divide any of these, then this sequence here, so the sequence here, is decreasing. Okay? So this is the very tricky part of this question, is because, again, here it's very easy to just apply the induction, but if you're here where you don't have any more divisibility, coming up with this idea of looking at all of these valuations and seeing they're decreasing is the tricky bit of the problem. And I think this makes what makes the problem hard. Okay, so how are we going to show this? So let's start looking at this quadrilateral here. Okay? So I want to say something about this diagonal and this diagonal, right? So I want to look at these two things here. I know that this guy, squared, this has a p to the t. This has a p to the t. This has a p to the t here. So if I want to compare these two, if you're in a quadrilateral which is cyclic, what's the easy relation that you have in a cyclic quadrilateral? Well, the only one that you can learn in a very early age, which is not, what I wrote with Brahmaputra's formula, but rather Ptolemy's theorem. So we will use Ptolemy's theorem. Okay, so let's write it up. So what do we have? Well, these are the diagonals. So you have A1, A3 times A2, A4. This is equal to A2, A3 times A1, A4. Okay? Plus A4, A3 times A1, A2. Okay, so let's see what I want to get. I want to look at these two things here. I want to compare A1, A3, the valuations. So I want this and A1, A4. So I want this and this. Okay, so the trick is, let's move this part here to the other side and square it. So move that one to the other side and square it. We have A1, A3 times A2, A4 minus A4, A3 times A1, A2 all squared. This is equal to A2, A3 squared times A1, A4 squared. Good. So now let's expand it out. So you have A1 squared, A3 squared times A2 squared, A4 squared plus A4, A3 squared times A1 squared, A2 squared minus 2, let's say, doesn't matter the order, A1, A3, A2, A4, A4, A3, A1, A2, and this is A2, A3 squared times A1 squared, A4 squared, okay? So that's the relation after you square it. Okay, so what do we do with it? Well, let's observe that this guy is an integer, right? So this is an integer, this is an integer, this is an integer, so that means this guy here, it's also an integer. Good. So we can naturally talk about divisibility. So let's look at the divisibilities by p to the t. Okay, so let's look at valuations. Well, the valuation in A4, A3 squared times A1 squared times A2 squared, well, these are two sides, right? I have a p to the t here and a p to the t here. So that's p to the 2t, so this is 2t. What else? Well, the valuation in A1 squared, A3 squared, times A2 squared, A4 squared, this is going to be Okay, so it's an A1, A3. So this is a diagonal, A2 squared, A4 squared. Again, I do not know. So let's just leave it like that. So A1, A3 squared plus A2 squared, A4 squared. I do not know how to compute this, but let's note that whatever it is, because I assumed that no diagonal squared is divisible by p to the t, this number is strictly less, anyways, less or equal to 2t minus 2 if I want to be more precise. Okay? So this one is like that. And now let's look at this one here. So we have the valuation inside this integer, which is A1, 3, A2, A4, A4, A3, A1, A2. What would this be? Well, it's A1, A3, I have it here, A2, A4, I have it here. So if you look at it, this is going to be T plus this VP of A1, A3 plus VP of A2, A4 over 2. Okay? Why is that? Well, again, these are sides. So the square of this, so again, remember this one has a T. So if you just square everything, so if I multiply it by 2 on this side, again, it's going to be what is written there. Okay, so this one squared has a T. Again, VP of A1, A2 squared, this is also T. And then you just manipulate the equations and you get that. Good. So now let's compare all of these numbers. So we have these 3 numbers. Okay. Well, 2t is bigger than both of them. This guy, half of it, okay, so I claim that because these are both less than t, this is bigger than the sum VP A1, A3 plus VP of A2, A4. Okay? So that means the valuation on this side here is the minimum of all these numbers. So you have the valuation of exponent of p is the minimum of all of them. So that means the exponent on this side here will be just equal to this, right? So exponent of p, okay, which means the VP. So this means in the left-hand side here is just going to be A1, A3 plus the exponent in A2, A4. Okay? And what is it on this side here? Well, this is going to be A2, A3 squared, A1, A4 squared. So this is going to be, the same thing in right-hand side. Let's just write it out. Well, this is going to be, so I have VP of A2, A3 squared times A1, A4 squared. So I just add them up. So I have A2, A3 squared plus VP of A1, A4 squared. And this is equal to T. Okay, so this is T plus VP of A1, A4 squared. Okay? So I have that. Sorry, this one was with a square, right? I was missing some squares here. Yeah. Sorry about that. Okay. So let's just write what the formula for A1, A4 squared is. Well, this is VP of A1, A3 squared plus VP of A2, A4 squared, and then it's going to be minus this t here. Okay, but whatever this is obviously going to be negative, so that means this guy is below this, okay? So I get that VP of A1, A4 squared, this is less than VP of A1, A3 squared. And now I can continue this procedure. I mean, I'm not going to write all the details. It's the same idea. I played around with this quadrilateral. Now I move to this. And it's the same sort of inequalities. So if you do the same sort of inequalities, you have the justification that the sequence is decreasing. So I just showed you an example of the computation. It's literally the same thing if you continue doing this. It's an induction process if you want. So you continue doing this, and you get that the sequence is indeed decreasing. And why is this a contradiction? Well, let me write it for you to see. So you have VP of A1, A3 squared. This is bigger than VP of A1, A4 squared. And then you go around until you reach A1, AK squared. Okay? But this is t, and wherever you started was less than t by assumption. Okay? And there's no way that could happen if you have that, okay? Good. So that's all I want to say about the solution. I think this idea of looking at the valuations, it's appeared in a ton of IMO problems recently, especially IMO shortlist and even IMO problem, looking at the valuation, estimating valuations, and these kind of tricky inequalities with valuations. Similar sort of problem with doing careful estimation about valuation was on IMO 2018 problem 5. So again, this idea of doing inequalities and estimating carefully the valuation is again a very useful idea. And again, in combo geo problems, dividing your problem into pieces and, you know, seeing what happens is also useful. So these are the main ideas in the solution. And that's all I would have to say about it. But if you have questions, I'm happy to answer them.
All right, let's thank Vlad for his talk. And now, if you have any questions, please raise your hand.
So you had that polynomial
Yeah,
for...
let's put it up again.
Yes. And you said that the formula is not known for heptagons, for examples.
Yeah, I don't know recently if there has been done anything for heptagons, octagons. I haven't checked the recent literature. But again, we know, some property of this polynomial, but not an explicit description of what it is.
But we know the degree of it.
Yeah.
And it means that if we test it with enough heptagons, we can find the relations between the coefficients. We can plug it into a system of
Yeah, I assume so. So I think you're right. For the first, I don't know, some acceptable values, you can probably do that. But I think, once you get, I don't know, let me get a number, 100, you might run out of battery for it.
Oh, okay.
Yeah,
That's
so
more optimistic than I thought.
I don't know. I mean, depends on your computing power, but yeah.
How fast does the degree grow?
Yeah, I can show you what the... No? Sorry, it was back. Yeah.
Okay.
Yeah, so the degree growth is just exponential, if you look at it. Because you have Stirling's formula, that's like 4 to the m. Yeah.
Okay, okay.
Yeah.
Yeah, thank you.
Other questions, please? Questions? You're saying hi or you want to ask a question? I saw your hand waving. When I see a hand, then I assume that you want to ask a question. All right, if there are no other questions, let's thank Vlad again. This resumes all our IMO showcase lectures. Thank you.